Welcome back. In our last video, we introduced the idea of conditional probabilities, and then we lumped those in with everything else to show that there are many different ways of calculating probabilities that you're asked. You can use a two-way table, a Venn diagram, or a tree diagram. And which way works best depends on what you like best, because given any of those, you can use any of the others. So, I thought we could start this video with an example here where you're not given any displays and you have to create your own. So let's look at this example here. So, if you want, pause the video now, try to work through this problem on your own parts A and B. If you don't want to, or you just want to see how it works, that's fine. But I want to give you the opportunity to work on it yourself if you can. But I'm going to walk through from beginning to end how I would attack this problem. So in January 2017, 52% of US senators were Republicans and the rest were Democrats or independents. 52% Republican and the rest were Democrats or independents. So if 52% is already taken, what's left is 48. Okay, I'm going to assume that these letters are not going to be reused for other variable names later, hopefully. Okay, 21% of the senators were females, and 47% of the senators were male Republicans. All right, so 21% female. And 47% male Republicans. Okay, so suppose we select one of these senators at random, define events. R is a Republican, and M is male. Good, I've already done that. Part A asks us to find the probability of Republican or male. Republican or male. Unfortunately, that's not one of the things we've written down here, so we've got to find that. So, let's see. And you could drive yourself crazy trying to figure out what the probability of Republican or male is. Given this information, it seems like some kind of complicated logic problem. But once you realize that any type of probability like this is much easier to calculate with an appropriate display, that gives you a plan of attack. Now, since I'm doing this problem, my favorite display is a two-way table. And so I would imagine, given this information here, we've got everything we need to completely figure out the two-way table. Once we have that, we should be able to find this probability or any other. All right? So, we're going to leave that chilling there. We're going to make our two-way table. So, for our two-way table, we've got two variables. We've got gender, and then we've got political affiliation. So, I'm going to put gender across the top. And then we've got the political affiliation along the rows here. So we've got Republican. Now, it would be a mistake to put Democrat and Independent on separate rows here, because in the information we're given, Democrat or Independent was all lumped together. So that's the way you should display it here. And I know when we're talking about probabilities, or usually means or of two separate things, but here, these are all being lumped together, so we'll treat them as one. Okay, so let's start filling in what we know. Well, we know for sure that this is going to be 100% grand total. All right, so we're going to be putting in percentages in all these places. So starting from the top here, 52% are Republican. So that is the Republican total here, 52%. And what we wrote here was the other 48% had to be Democrat or Independent, and it does turn out that had to be 48% anyway. Good. We also know that it's 21% female senators. So that's total is 21 here. So what does that allow us to fill out that isn't necessarily over there? Then the percentage of male senators has to be 100 minus 21, which is 79. All right. So we have all the marginal totals for both variables. All we really need is one of these four. And from there, we should be able to fill out the rest. So we know 47% of senators are male and Republican. That's this cell here, 47%. And that is the key that unlocks all the rest. Because now we just subtract. 79 minus 47 is 32 here. 52 minus 47 is just 5% here. And either 48 minus 32 is 16, or 21 minus 5 is 16. This is why the two-way table, I think, is the best display. You'll always be given enough information to create it. Tree diagrams, sometimes you're not given exactly what you want for how you want to create the diagram. And Venn diagrams, they are easy to construct, but some questions can be harder to answer using the Venn diagram. I think the two-way table is the best of both worlds. But once we're done with the problem, I'll show you what the relevant tree diagram and Venn diagram would look like for this problem. But now that we have this, we should be able to answer this question. What is the probability of Republican or male? Republicans are everyone on this row. Males are everyone on this column. But if you try and add these two numbers together, these two percentages, you're going to get 131%. I don't think 131% of senators are Republican or male because that's impossible. So, again, you could take these two and add them together, but then you have to remember to subtract the cell that represents both, or you could take all the cells that represent Republicans or males and simply add those numbers together. So that's what I'm going to do. So that's 79 and 5 is 84%. 84%. Okay. So, again, being able to calculate this is fine. If you were asked to interpret the value in context, which you happen to be asked, then you would say 84% of senators are Republican, male, and we're including the probability that they are both. Right? So that's an interesting thing to notice in this course, is that if you're asked for the probability of the or of two events, it's what we call the inclusive or, and it includes the probability that it is also both. This is not the exclusive or, where it has to be Republicans or males but not both. That would just be these two cells. It is inclusive. It includes the and probability as well. Okay. So that's part A. Part B asks, consider the event that the randomly selected senator is a female, Democrat, or independent. Write this event in symbolic form and find its probability. Okay, so the randomly selected senator is a female, Democrat, or independent. Write this event in symbolic form. Okay, so it wants you to write the probability in like this format. And they really only ever told us how to define the events for Republican and male. So it's kind of unclear whether we should be writing this in terms of these definitions or whether we can create our own for female or Democrat or independent. And I think it's pretty reasonable to use these denotations, so we'll just write it that way. So the probability the randomly selected senator is a female, Democrat, or independent. So is this like an or an and, or what? Well, a female, Democrat, or independent has to be female and Democrat and independent, right? So this is female and D or I. And I'll go ahead and put that in like quotation marks because I don't want people to get confused that or is like another probability here. So what is the probability that a randomly selected senator is a female and Democrat or independent? Well, we can look through our two-way table that's complete here, and they have to be female in this column, Democrat or independent in this row. The only cell that's both is this one. And it turns out to be the only one that we didn't consider for this problem, because all senators are either Republican, male, Republican and male, or female and Democrat or independent. Those are the only four choices. So this is 16%. If you didn't have the two-way table, I suppose you could have arrived at this by knowing that these two events were complements of each other and calculating this probability as 1 minus 84%, which would still give you that 16%. So again, even if you're not given a display, a two-way table, Venn diagram, or tree diagram, you can create one. And I would recommend making the two-way table so that you can answer questions like these. I think it's the easiest way to do it. And creating the two-way table, as long as you have confidence that you have all the information you need, which you almost certainly will, that should give you the confidence to be able to construct that and answer those questions. Let me also show you what the tree diagram and Venn diagram would look like based on the information you were given in this problem. So let's say you weren't terribly comfortable creating the two-way table from the information in the problem, and you wanted to make a Venn diagram instead. I think this is the way that they would want you to have made that, because what they gave you to define is Republican and male. So those should be your two circles. They gave you the probability of male and Republican, so that 47% is the intersection or overlap. From there, you know 52% are Republicans total, so that entire circle is 52%. You've already got 47% in there, so that has to be the other 5%. And then to figure out this number, you know 21% are female. That means the other 79% are male. So these two numbers would have had to add to 79, and you already had this one. So making this, it requires you to do some work with these values, and then once you have this, I suppose getting this probability was pretty easy. You just add these three numbers together. But then to answer part B, you would have to know instinctively that this was the complement, or you would have had to add all these up and then be like, okay, this probability here has to be the other 16%, and it represents female and Democrat or independent. It's not super obvious. I think it's easier to see in the table. For the tree diagram, and again, I try to avoid tree diagrams unless I'm being asked something about conditional probabilities, which was not the case here. There is no vertical bar, there are no givens here. I would really avoid using this unless there are conditional probabilities because it can be hard to fill it out. Based on the information we had, if you put male and female as your first split, you're given 21% female, which means you also know 79% is male. All the other information kind of helps, I guess. You can use this 47% male and Republican to figure out that that is here. That's not this probability. Because this would be the probability that you're Republican given that you're male. This is the and, so it actually goes out here. Filling out the rest of the diagram requires a lot of filling in the blanks yourself that you didn't really have to do here. if you know that it's 52% Republican total, and this is 47%, this is the other 5. From there, if you have this probability and this one, you can figure this one out, but it requires you to do 47% divided by 79%. And that is 59%. And that opens the door a little bit. You know that this is then 41%. Once you have these two, you can fill in this by multiplying. 0.79 times 0.41 is 32%. You can then use these 3, add them up, subtract from 1 to get this one. So that's 47 plus 32 plus 5. That's the 84% that is going to be this. This is the other 16%. And then you would do the whole division deal again here. So this is 5% over 21%. 5 divided by 21. That's 24%. And this is 76%. Okay. And from there, to answer the questions, probability of Republican or male, you would have to know to add these 3 together. And for female and Democrat or independent, that one was pretty simple. But filling the tree diagram out took a lot of work. More, I think, than the two-way table. So that's just to show you, I really do think the two-way table is the best display if you are given information and have to answer these types of questions. So, let's change gears and talk about something else. So let's go back to the idea of independent events. What does it mean again for 2 events to be independent? That means, like, they don't affect each other, right? And we could be a little more formal with our language there. We could say the occurrence of one event does not affect the occurrence of another event, for instance. Okay? But it's that general idea. So here's a scenario. Suppose you roll a fair die, normal 6-sided die, and you get a 1. And then you roll again, and you get a 2. Are the results of these 2 events independent of each other? It appears yes, right? The die has no idea that the first roll was a 1. It shouldn't affect what you get the next time. So if you think they're independent, explain using probabilities. So it's easy enough to just say, well, duh, the second roll isn't affected by the first. But let's prove it. Let's actually show that they are independent. And I think we could start showing that by just saying, hey, what are the probabilities of those events? So what is the probability of rolling a 1? 1 in 6. The probability that you roll a 2, also 1 in 6. How about this? What's the probability that you roll a 2 given that you just rolled a 1? It's still 1 in 6, right? Like we just said. These 2 events appear to be independent. The fact that we rolled a 1 makes no difference. So the probability of rolling a 2, given that we rolled a 1, is still 1/6, which is the same as the probability of rolling a 2 without any knowledge of what we rolled before. This is the idea behind independent events. So this is what we saw here. The probability of getting a 2 given that you rolled a 1 is the same as the probability of rolling a 2 without any information. So these two probabilities are equal. And that's what it means for two events to be independent. Events A and B are only independent, well, if and only if. That's the strongest form of that. That's if the probability of A given B is equal to the probability of A, and if you reverse all the letters, it's still true. The probability of B given A equals the probability of B. You can interpret this as, given the information that B happened makes absolutely no difference, the probability of A, given that that happened, is still just the probability of A. B has no effect on A. Right? That's what it means for the events to be independent, and it works both ways. A doesn't depend on B, B doesn't depend on A. So, I want you to notice, we had this kind of idea for independence before, that they don't affect each other. We now have a quantitative, cut and dried rule for determining whether two events are independent. And that's if this is true. So, from now going forward, if you're asked whether two events are independent, don't give an English explanation. That's not what they want. They want this. They want this. Now, this is different than, you may remember a long time ago with two-way tables, we asked whether two variables were independent. That's different than this. This is only talking about specific events. Okay, we'll get to whether two variables are independent again later in the class. But for now, we're only talking about independent events. Okay? And this is how you check it. So let's see this in action. Okay, so let's work on an example that you probably knew how to do, I don't know, like 6-7 years ago, but you didn't know the formal rules of probability. But let's see how it goes now. So suppose you have 5 green marbles and 4 red marbles in a bag. 5 green, 4 red. What is the probability of drawing a green marble out of the bag and then drawing a red marble from those remaining? So you can interpret that as you take the green one out, put it off to the side, then grab a red. Okay. Now, you don't need to know any probability rules to answer this question. But since you do now, let's see if we can use those to help understand why it is the way it is. So, we want to know the probability of getting green and then red. So we can write that. And this is not really telling the whole story, right? Because you're taking the green marble out of the bag, putting it off to the side, then taking the red. So this is really two events, and it would be easier if we wrote this as a series of two different events. So this is really the probability of green and red, given that green already happened. Red, given that you took a green out. So it's really like this. And remember, this means and. Okay. So if we've got the probability of two events with an and there, that means we multiply. Sorry, I'm capitalizing green each time, but not the other one, so I'm just going to fix that, because I don't know if it makes you anxious or anything, but it does to me, kind of. There we go. Okay, so we're just multiplying the probability of green times the probability of red, given that green has already been taken out of the bag. What's the probability of getting green first? Well, there are 5 green marbles out of 9 in the bag, so 5 and 9. And means multiply. So, what's the probability of getting red given that we already took a green out and it's out of the bag? Well, How many red marbles are there? 4. How many marbles are there left in the bag once we take the green one out? Well, we start with 9, take one out, that's 8. So this is 20 over 72. And again, I know that can be reduced, but I don't really care. I just don't care. 20 out of 72 is the probability of that. So, wait. Are these events independent? And by these events, I'm referring to the first marble you take out of the bag and the second one that you take out of the bag. Are the first and second draws independent events? Maybe you already know the answer, but I don't want you to answer in English. I want you to answer using probabilities. How can you show whether the first and second draws are independent events using probabilities? Well, our two events are the first draw and the second draw. So those would be A and B. So let's see here. If those two are independent, then the probability of red second, given that you took a green out first, should be equal to red second, green first. This would be red second, right? And really, if we're considering it by itself, this is just the probability of getting red out of the bag from the very beginning. If these two events are independent, then this should be true. Is it? Well, the probability of getting red second given green first, that was this. That's 4 over 8. The probability of getting red out of the bag from the very beginning, 4 out of 9. Those are not equal. So as a result, these two events are not independent. The probability of getting red second is dependent upon the fact that you got green first. The denominator changed because you took a marble out. Right? So how could we change the process of how these events occur so that the first and second draws are independent events? Well, it seems like the issue here is this is changing from a 9 to an 8 because we took this marble out. So what if we just drew a green marble and put it back in the bag and then drew a second one? That would make all the difference. The problem we started with had us taking a marble, and when we chose it, we took it out of the bag and left it out before we drew the next one. This is what is called drawing without replacement. You also see this if you are choosing cards out of a deck. If you take a card, look at it, put it off to the side before you draw the next one, you didn't replace the card. You drew without replacement. When you do that, you're reducing the number of marbles or cards that are left every time you take one out. So those probabilities are going to change. When you draw without replacement, those events cannot be independent because those probabilities change. So these are not independent events. In contrast, if every time we were to take a marble out of the bag, we put it back and like jumbled them up again so they were randomly scattered or whatever, and then chose another one, then this would still be 4 out of 9. It wouldn't matter what color we drew first because we put it back. If you take a card out of a deck, look at it, put it back in the deck, shuffle them up, draw again, all the probabilities of drawing particular types of cards are the same. So if we draw with replacement, those events would be independent. So, this is important. It's really the case for everything that I teach, but particularly for things like this. I do not want you to memorize this. I don't want that. Because there is virtually no chance that you'll remember that come May when you take the AP test. I don't want you to memorize it. I want you to understand it. I want you to be able to rationalize in your head why, if you draw without replacement, if you take those marbles out of the bag, why those probabilities change and why that means that those events are not independent using this. It's because these are not the same. Whereas if you draw with replacement, those probabilities remain the same. This is true, and those events are independent. Okay, don't memorize. Understand. And if you have trouble understanding a concept, some of these things are not easy, right? Probability is probably one of the units in this class that is most misunderstood, most confused, because you already have some prior knowledge that if you actually have misconceptions, it's really hard to break those misconceptions and start over, right? So if you have these ideas in your head, it can be hard to get them out. Maybe some of these concepts aren't really sticking. I'm willing to try and reorganize how I teach these things if you need it. If you're struggling with something, just let me know, right? I'm more than happy. It is literally my job, and I love doing it, to help people understand things. If you memorize, you'll forget. I don't care if you get A's on the tests in this class. It doesn't matter. The grades, whatever. I want you to understand. Okay, that's what I'm going for here. So, in this video, you learned quite a bit. We reviewed how to use two-way tables, but also, if you want, Venn diagrams or tree diagrams to answer questions about probability. And we've covered independent events. What does it mean for events to be independent? It means this. We're trying to get away from this idea now. We now have a calculation we can use that we can point to. So we'll use that, and we saw how it works in action and how it relates to drawing with or without replacement. So there will be one more video in Chapter 14, and after that, you'll have some time to work on the Chapter 14 homework. Make sure you look on Canvas for those due dates. And I think that's it for this one. So we'll see you next time.